Assalamu alaikum everyone. Welcome to Edexcel IAL A2 Physics Classroom. Before get going, I convey my apologies for the sound quality and the video quality because the microphone I had actually came out dead and I couldn't arrange a new one because we all are locked down due to coronavirus pandemic. Okay, let's start. Today we are going to discuss about electric field and this is the part one of this video, and this topic is contained in your Edexcel IAL or A2 physics syllabus in unit 4 and topic 6A. Okay, this is the first part of our electric field, and in this lecture we'll be discussing about these contents, and we'll be able to understand what an electric field is and a use of electric field in X-ray machine, what are electric field lines, what is the electric field strength, what electric potential is, what is the potential difference, and we'll discuss it in detail what actually potential difference is, and uniform field, we'll investigate an electric field. Then we'll discuss about uniform and radial field, and finally we'll combine some electric fields. Okay, let's start. First, electric field. What is an electric field? For example, suppose this is a magnet, okay, and from our previous idea we know that there is a region around the magnet, or region of space or volume of space around the magnet within which its magnetism can be detected. And if you bring some magnetic material or other magnet within this field, the magnetic material or the magnet will experience a force, and the magnetic material or the magnet will be accelerated. Okay, and the direction of acceleration will be determined whether it's a magnetic field or a magnet. If you bring a north pole directing towards it, then it will be accelerated in this direction. If you bring a south pole near its north pole, then it will be accelerated in this direction. Okay, the direction of the magnet or magnetic material will depend on which pole is actually brought near the permanent magnet or the magnet for which the field is created. Like this, if we have a charged particle or a charged object, there will be a volume of space or region of space around it within which other charged particle will experience a force. Okay, suppose you have brought plus q coulomb charge within this field, then this q coulomb charge or this charged particle will experience a force. That's why it will be accelerated. That's why an electric field, and the electric field is actually for this charged particle, like the magnetic field we discussed earlier. So an electric field is defined as the region of space or volume of space within which another charged particle will be accelerated. That means other charge or any other charged particle will experience a force. I'm repeating it again. The region of space or the volume of space within which any charged particle experiences a force, or that's why it is accelerated, is called an electric field. Okay, this region of space or the volume of space is defined as an electric field. Okay, now we'll see a use of electric field in X-ray machine. this is a metal target, tungsten. Okay. Now, suppose this is at 0 volt and this plate is at plus 45,000 volt, and with respect to this plate, the 0 volt plate is actually acting as a cathode, because with respect to plus 45,000 volt we can consider 0 volt a negative one, and in this machine electron is released by thermionic emission from the cathode, and since these two plates are at different electrical potential, there will be an electric field between them, and this field is a uniform field. Okay, you must remember that an electric field exists between any two charged particles, and the direction of the field will be from positive to negative, like magnetic field directing from north pole to south pole, and electron is emitted by thermionic emission from the cathode and will be accelerated in this direction. Okay, since it is positive and being accelerated highly, it will move in this direction and crash on the metal target. When electron, high speed electron or high energetic electron crashes onto some metal target, X-rays are emitted. So look, first how the X-rays are generated. When fast moving electrons are bombarded onto some metal target, the metal atoms absorb the energy from the electron, that is the kinetic energy of the electrons, or we can say when a fast moving electron is stopped by a metal target, the kinetic energy of the electron is absorbed by the metal atom and X-rays are emitted from the metal atoms. That's how X-rays are generated in X-ray machine. Later these X-rays are collimated to form parallel beam of or parallel rays of X-ray. Okay. Now electric field lines. Okay. What are electric field lines? Like magnetic field lines, we know the magnetic field line or the magnetic field lines show the direction in which a lone north pole will be accelerated, or we can say the direction in which a north pole will experience a force, and to visualize the electric field, we draw some lines, and these lines show the direction of the electric field, and the direction indicates in which direction. The direction will be from positive to negative plate, or from positive terminal to the negative terminal. And now we can define electric field lines or electric force lines as the lines directing towards, or the line or the direction in which a positively charged particle will be pushed. In case of magnetic field, the magnetic field lines show the direction in which a lone north pole or free north pole experiences a force or accelerated. And in this case, in the case of electric field, the electric field lines are the lines that show the direction in which a positively charged particle will experience a force, or a positively charged particle will be accelerated, the direction in which the positively charged particle will be accelerated. Okay. So now electric field strength. we have discussed about electric field, use of electric field lines. Now, electric field strength. Suppose this is a positively charged particle and there will be an electric field around the charged particle, or there will be a region of space around it in which other charged particle will experience a force. And since it's positively charged, the direction of the field will be outwards. These are the electric field lines, and this is the electric field for this particle. And if you bring some charged particle having a charge of Q, the charged particle will experience a force when it is within the field, and the direction in which it will be accelerated depends on the sign of the charge. If it is plus Q, then it will be pushed in this direction, or from or we can say outwards from the field. And plus Q coulomb charge, since it is accelerating in this direction, that means it is experiencing a force, and consider this force as F. Okay, so we can say that Q coulomb charge experiences a force of F. Then unit coulomb charge will experience a force of F by Q, and by definition this is the electric field strength E, F by Q, and this is the electric field strength of this particular point. Remember, electric field strength is not constant for all type of electric field. Only within a uniform electric field, the field strength will be same everywhere within the field. But in case of radial field like this, electric field strength will vary from place to place. And when we define electric field strength, we define it for a particular point within the electric field. So now we are going to define electric field strength. Okay, listen. Electric field strength of a particular point in an electric field, I'm again repeating, electric field strength of a particular point, suppose we are considering this point as A. Electric field strength of a particular point within an electric field is defined as the force experienced by unit charge onto that point. Okay, the force experienced by unit charge onto that point is called the electric field strength of that particular point of the electric field. And if we consider that the object has negative charge, okay, then the direction of the field will be inwards. You have to remember that the direction of electric field is always from positive to negative. Then now we have the formula of electric field, and electric field E is equal to F by Q. Therefore, the SI unit of electric field strength E is equal to F by Q. Therefore, the electric field strength has the unit Newton per Coulomb. This is the SI unit of electric field strength. Electric field strength has another unit, that is volts per meter, and these two units are equivalent, and this unit is actually defined from the uniform field, and we'll discuss it later how it comes. Now we'll be able to calculate the force experienced by any charged particle when it is within an electric field. Suppose the particle has a Okay, let me use different colored marker. The particle has a charge of Q. Then we know that electric field strength is equal to F by Q. Then if you want to find out the total force, because electric field strength is defined as the force experienced by unit charge per coulomb charge, and if you want to calculate the total force experienced by Q coulomb charge subject F, you will get EQ. This is the total force F experienced by the charge Q when it is within an electric field, and the field strength of the particular point in which Q has been brought is E. Okay, now we know that, and this is the force that is causing Q coulomb charge to accelerate. Therefore, we can say that this is an unbalanced force, and for an unbalanced force, we have an equation F is equal to ma. Then, if we equate these two equations, we find ma is equal to EQ, and subjecting A, we find EQ divided by m. This is the equation for the acceleration of the charged particle Q, and m is the mass of the charged particle. If the charged particle is an electron, then you can find the acceleration by putting the value of E into charge of the electron, that is 1.6 into 10 to the power minus 19, and mass of the electron, that is 9.1 into 10 to the power minus 31 kg. Okay. Using this equation, we will be able to find out the acceleration that is experienced by an electron when it is within the electric field. Before that, you have to know the electric field strength of that particular point within the electric field. Now we are going to discuss about electrical potential. Again, consider a charged particle, okay, and there will be an electric field around it, and field lines directing outwards from the center. Okay. Suppose you want to bring some charged particle into the electric field, and the charged particle has a charge of Q. Okay. If it has a charge of plus Q, positive charge, then when it is brought into the electric field, it will experience an outward force, and if this has a charge of minus Q, then it will be accelerated towards the charged particle. And ignoring the sign, just to consider Q coulomb charge, suppose you want to bring some Q coulomb charge into this point, and this point we are denoting it with A, and this is another point B. Okay, look, if it is plus Q coulomb charge, when you want to bring it into the point A, it will be pushed outwards. Therefore, you have to do some work. You have to do some work to bring the plus Q coulomb charge into the point A, and the charged particle will start experiencing force when it just enters the field, and outside the field we'll consider it as an infinite distance. And if it is minus Q coulomb charge, then it will be accelerated towards the field. That means work is done on the Q coulomb charge. Okay, now ignoring the sign, let us define what electrical potential is. If you want to bring Q coulomb charge into the point A, Q coulomb charge into the point A, then the work done or energy transferred to q coulomb charge to bring into the point A from infinite distance. From infinite distance means from outside the field, is actually defined as the potential of the point, and we'll denote it with VA. Okay, so electrical potential or electric potential is defined as the work done or energy transferred to q coulomb charge. Okay, and suppose you have brought q coulomb charge into point A, and suppose the work done onto q coulomb charge is W, or the energy transferred to the q coulomb charge is E. Then we can write, for q coulomb charge, work done is W or energy transferred is E, and for per coulomb charge, for unit charge, the work done will be W by Q or the energy transferred will be E by Q. And by definition, W by Q or E by Q actually is the potential of that point. So electrical potential V is equal to W by Q or E by Q. So what is the definition of electric potential? Electric potential, before going to define electric potential, let us consider a different point B. If you want to bring q coulomb charge into point B, you have to do more work since it is closer to the charge particle and the field lines are closer, more dense as you go towards the charge particle. That's why the field is becoming stronger, and so you have to do more work if you want to bring q coulomb charge into point B. Therefore, if the work done on per coulomb charge to bring into point B is WB, then the electrical potential of VB will be defined as WB by Q, or energy transferred by Q. Okay, the point is at different electrical potential, and the potential of this point is VB. So what is the definition of the electrical potential? Now will be the electrical potential of a particular point. For point, the electrical potential is defined either for point A or point B. So if you define point A or any point, the electrical potential of a particular point within an electric field is actually defined as the work done or energy transferred to unit coulomb charge to bring onto that point from infinite distance. So the potential of point A will be the work done on per coulomb charge or energy transferred on per coulomb charge to bring into point A from infinite distance, and the electric potential of point B will be the work done or energy transferred to per coulomb charge to bring into point B from infinite distance. Then we have the definition of the electric potential. What it is? The electric potential of a particular point within an electric field is defined as the work done or energy transfer to bring unit charge into that point from infinite distance. And since the electric potential of these 2 points are different, if you connect it with a conductor, you will find current flowing from point B to A and electron flowing from point A to B. Okay, so to get current going, you have to have potential difference, and this is the potential difference. So what is the potential difference? The potential difference between point A and B, that is VAB, will be VB minus VA, higher potential minus lower potential, since in this case B is at higher potential. So, and simply we write it V as potential difference is equal to VB minus VA. So that will be the work done to bring unit charge or to transfer unit charge from point A to B. So what is the potential difference? Potential difference is actually defined for two particular points. So the potential difference between 2 points is the energy transferred or the amount of work done to transfer unit charge from one point to the other point. And when there is a continuous potential difference, there will be a continuous flow of current. So for current get going continuously, you have to maintain a potential difference between the 2 points, and that's why PD is required for continuous flow of current. Again, if the particle has a charge of minus, then you will find the potential difference V or VAB, and that will be VA minus VB, because in that case VA will be at higher potential and VB will be at lower potential, and the direction changes depending on the sign of the charge. So we have discussed about electric field strength, electric potential, potential difference. Now we are going to discuss about uniform field. So another thing I forgot to explain, the unit for potential difference is equal to, we had the formula V is equal to W by Q or E by Q. So the SI unit of the potential difference will be volt, and this will be actually joule per coulomb, since W or E has the unit joule and Q has the unit coulomb. Now we are going to construct an electric field, and for this you will need 2 metal plates, parallel metal plates obviously, since you are setting up an uniform electric field. Uniform electric field. Okay. Connect this with a power supply, and this is EHT, and EHT stands for extra high tension. Okay, and this is the power supply we made in this case, and by adjusting it you can set up an electric field. This is the positive and this is the negative terminal, so this will be at plus 2000 volts. The potential of this plate, this is not the potential difference or PD or not the voltage. This is actually the electrical potential at which the plate is. Okay, and this is minus 2000 volt. So the PD between these 2 plates is equal to higher potential minus lower potential, and that will be plus, or the potential difference actually, so you don't need to mention the sign, 4000 volt. Okay, EHT, and there will be electric field lines directing from the positive to the negative plate. This is an electric field, and you have to remember that an electric field exists always. Always an electric field exists between 2 charged objects or 2 charged particles. Okay. Sorry, I forgot to mention another thing. there will be an electric field between two charged particle or charged objects if the plate or the objects are at different electric potential. If this is at plus 2000 volt and this is at plus 2000 volt, there will be no electric field between these two plates because the plates are at the same electric potential. So you have to remember that an electric field exists between two plates if the plates are at different electric potential. In this case, the plates are at different electric potentials. This is at plus 2000 volt and this is at minus 2000 volt. That's why there is an electric field between the plates. And look at the diagram. The field lines are parallel and equi-spaced. The spacing between the lines are equal. This indicates a uniform electric field. In an uniform electric field, the field lines are parallel and equi-spaced. And what are the speciality about this uniform electric field? In this case, since the field lines are everywhere equi-spaced and parallel, the field strength is the same anywhere within the field. So in a uniform electric field, the field strength is the same for every point within the field. Okay. Now we are actually discussing about another important thing, that is the equipotential. Okay, let me draw a broken line. If we move across this line, okay, this plus 2000 volt and this is at minus 2000 volt, so along this line the electric potential will be 0 volt, and along this line it will be plus 1000 volt and this will be minus 1000 volt. These lines are called equipotential. The line connecting the locations, those are at the same electric potential. If you move across this line, you will find no potential difference because all these locations are at the same potential, that is at 0 volt, and if you move along these lines, you will find no potential difference because all these locations or all these points are at the same potential, that is plus 1000 volt, and this line minus 1000 volt. These lines are called actually equipotential. And you have to remember that in a uniform field, the equipotential are equi-spaced as well. Okay, and the equipotential actually refers how rapidly the potential changes or varies. And in this case, the equipotentials are equi-spaced, so the potential is changing uniformly with distance. And if you want to find out the field strength of this uniform field, suppose the plates are placed at a distance d. The separation between the plates are d. Then the field strength of this electric field will be E is equal to V by D. And from this equation, the field unit, another unit that we wrote before, volt per meter, actually came from. Okay, this is another formula for calculating electric field, and this is applicable only for uniform electric field. Okay, now we are going to investigate an electric field. Uniform field has been explained. To investigate an electric field, actually we are investigating a uniform field. So you will require, and I'm drawing a diagram from the top view. Okay, suppose this is a container containing castor oil. Okay, container and it has castor oil within it. Now place two metal plates within the castor oil or within the container, connect it with an EHT, and before turning on the power supply, suppose the switch is still open, before turning on the power supply, put some semolina grains or sprinkle some semolina grains onto the castor oil. Okay, suppose you have sprinkled some semolina grain evenly or as you want, some semolina grain onto the castor oil. There is a specialty about the semolina grain and castor oil. You must remember that semolina grains become charged when it is placed within castor oil. Okay, semolina grains become charged when you sprinkle it or when you put them into castor oil. Since the semolina grains are charged, okay, we know that charged particle will experience a force within an electric field. Since the power supply is still turned off, there is no electric field in between, but when you turn on the power supply, there will be an electric field between these two plates. Since the plates are parallel, so there will be a uniform field between them. An electric field will be set up between the plates, and you will notice that the semolina grains then line up with the field. The semolina grain will line up with the field. Okay, that's how we can demonstrate an electric field or investigate an electric field, and this field is actually a uniform field. Investigating electric field. Now our topic to be discussed is uniform and radial field. We have already discussed about uniform field. Let us discuss again to compare it with radial field. Plus V minus V, and you have a charge particle plus nothing. So there will be electric field line from the positive to the negative, and you have electric field showing, indicating outwards. If you have negative charge onto the particle, the direction will be towards the charge particle. Okay, in this case, since it is positive and electric field strength or field line shows the direction in which a positively charged or unit positive charge experience a force, so the unit positive charge will be pushed outwards in this case. That's why the field is directing from positive to negative. And these are the field lines. And look at this diagram. This is a uniform field and this is a radial field. And in this field, the field lines are equispaced and parallel. So the field is uniform and the field strength is the same everywhere within the field. But in this case, the field lines are spacing out. So as you move outside the field lines are actually spacing out. So the field is growing weaker. Okay. Therefore, the field strength is not the same everywhere within the radial field. And in this case, we have equipotential. Those are also equispaced because the equipotential actually shows how rapidly the field strength changes, or we can say how rapidly the potential changes. Okay, and in this case the potential changes evenly with distance, and that's why we had the formula is equal to V by D. Okay, but in this case the equipotential will be like this. Sorry, look at the diagram. As you move outside the field or towards the outside the field, the equipotential are actually spacing out also. So we can say that the potential with distance, actually the potential is collapsing, or the potential is changing with a decreasing rate with distance, and in this case potential changes proportional or evenly with distance. So we can say that as we move through an electric field, the electric potential changes from plus V to minus V, or in this case suppose this is plus V and minus V outside the field. When we move through an electric field, the electric potential changes from place to place, and the locations, those locations which all have the same potential are the equipotential. These all the points within this line have the same potential. That's why it's an equipotential. And in this case, these are the equipotential lines. And look at the diagrams. The equipotential and the field lines are always perpendicular to each other. And you have to remember another important thing, that the field lines do not cross or intersect with each other. Now our last topic, combination of electric field. Sometimes a question arises, suppose when you have a charged sphere which is not hollow, which is solid, then actually we draw the field lines from the center of the sphere. Okay, if it is positive, then outwards. If it is negative, okay, I'm using another. If positive, then it is outwards, but if negative, then the direction will be inverse. Okay, so it is a solid sphere. What will happen if you have a hollow sphere, where the charges are distributed on the surface of the metal sphere? Suppose it's a hollow sphere. In this case, though the charges are actually evenly spread or on the surface of the metal sphere, but the field lines actually originate from the center. So always you have to consider the field lines from the center of the charged sphere, whether it is hollow or solid. Now, combining electric field, suppose this is a positively charged sphere, and in this case the field lines will be like this, and another, suppose this is a negatively charged sphere. Okay, in this case the field lines will direct inverse, and when we combine two fields, suppose this is a positive one and this is a negative one. Then the field will be the resultant field. Actually, when you combine electric field, you have to remember that the field strength at a particular point, the field strength at a particular point in a combined field is the vector sum of the field, or the vector sum of the electric field that each individual field can cause. Okay, so the resultant electric field will be okay, and there will be some just like a North Pole and South Pole placing alongside, facing each other, and this is a combined electric field between two oppositely charged spheres, and we have already showed the electric field between two parallel plates in the section of uniform field. Now, if you place two positively charged spheres, positively charged, and these two fields will repel each other. Therefore, the direction, okay, since the field lines do not cross or intersect, this is the combined electric field when two similarly charged sphere is placed facing each other. Okay, and in this location, look, there is no field line, so there is no field strength there. This is a neutral point, and the field strength at this point will be 0. Now, if we have, suppose this is arc and this is a positively charged particle, and the direction of the field will be, since it will induce, okay, you have to remember that since it is positively charged, it will induce negative charge on the earth surface. Therefore, the direction of the field will be like this. Okay, and if you had a negatively charged sphere, then similar pattern will be found, but the direction will be opposite. Okay, since the sphere is negatively charged, it will induce some positive charge near that surface, so the direction of the field line will be from positive to negative terminal. And now we'll be able to understand how a lightning conductor works. Okay, suppose this is the top or rooftop of a building, and the building has a lightning conductor which is spiked actually. So you'll see that, and suppose a cloud that is positively charged floating above it, okay, then it will induce some negative charge near the surface, and you have to remember that charges are concentrated at the spiked part, okay, where any object is pointy, or in a point of in an object where there is a point or sharp point or spike, there will be a buildup of charge or concentrated buildup of charge. Therefore, the direction of the field line will be and the direction will be from positive to negative. Look at this diagram. There is also field from the cloud to the earth, but since the charge is concentrated at the spiked part, the field lines are concentrated as well. The field lines are dense enough, so the field strength at this point is strong enough and stronger, much stronger than other part of the surface. That's why the charge is, or the charge on the cloud is attracted much more strongly towards that point than other points on the surface. So the discharging process is likely to occur from this point. Okay, that's why a lightning conductor is actually spiked or pointy. And another reason for a lightning conductor for being spiked, that is, since the charge, the charge builds up concentrated, or the charge that has been built up into the point is concentrated, charge can also leak from that point. That can leak from the pointy object and travel through this direction and can discharge the cloud. That's why actually that reduces the chance of lightning or thunderstorm striking the ground. Okay, that's it for today, and I hope you understand it, and let me know if you have some problem, and I'll be there to help you out. And since we all are locked down due to the coronavirus pandemic, and I'm also in home quarantine, and to stay safe, you must also stay at home, and stay at home and be safe, and pray for all. Okay, Allah Hafiz.